Hello, I'm Jimmy Lappink, psychologist and statistician, and I'm going to share a short video about how to perform a linear regression in R. I'm not going to focus on all the theory and assumptions underlying linear regression. There are loads of good resources on that already, but I'm going to share a few basic steps for doing the analysis in R. To keep this example short, I have simulated a dataset of 500 independent observations on a response variable or dependent variable y and a predictor variable x that reasonably meet key assumptions underlying linear regression. Both variables are quantitative variables with means of approximately 0 and standard deviations of about 1. If you've used R and RStudio before, you recognize that the interface I'm sharing on the screen is the one of RStudio. I'm using the free version of RStudio because it allows me to do all the things I want to do in R, and I like its adjustable multi-window interface. I have adjusted the interface such that the left window is for entering the code, and the figures or charts will appear on the right. So let's get started. First of all, we need a way to read the data. An easy way to do that is to make sure that you have saved your data in a so-called CSV or comma-separated values format. This is because R has a basic function to read CSV data files as you see here. The first line is just a note for myself, starts with a hashtag, and the second line is a command line which defines the data as a CSV file which is located in a specific folder on my device. Now we have to define the variables. We open the data file, but we have to define the variables. So the data file has a predictor variable x and a response variable y, which we can define as follows. We just, let's see, a note for myself, define variables and x as a column x in the data file that we just opened. If we want to see how many observations and missing values we have for x, variable x, well, we have in this case the length of x, which is the number of observations in column x. This is the sample size of x, 500. We have no missing data because the last line is a command for missing data, which says there is 0 missing data. Okay, we can do the same for variable y. Just repeat the comments that we have had, that we have used for variable x. We use them for y. We have 500 observations for y and 0 missing data. Now, before we want to continue with our analysis, we want to also create two other variables, which are the square and the cubic version, square and cubic version of x, x2 as x to the second power, and x3 is x to the third power. We will use them later on for quadratic and cubic regression models, but we have to define them before we can use them. So let's do that already. Now, before we actually run a linear regression, we check out the univariate and bivariate distributions of the variables involved. So let's start with the univariate distributions of x and y by simply asking for box plots and histograms. So, okay, let's make a note for myself. Here we're going to do univariate distributions box plot x. Hey, we see box plot x on the right. The reason, by the way, why I make notes, although they don't really serve as command language, is that, okay, when you do many analysis on a weekly basis, it is much easier for yourself if you go back to an analysis later on to see where you have the commands for instance, univariate distributions or for other specific functions. Also, if you share a script, which I tend to do, usually I save the code of an example that I've used in a text file. And if I want to share that with someone else later, then the other person can also see more easily all the things that I have done one by one. Okay. Let's go for a box plot of variable y, which is box plot of y. Well, this looks very similar to the box plot of x and not really strange histogram of x, which also looks like a fairly symmetric distribution. same as the histogram of y, looks at like a fairly symmetric distribution, no extreme cases that are far away from the rest of the distribution, which is fine. Now, okay, now that we've done that, let's look at the bivariate distribution and corresponding Pearson's linear correlation coefficient, which is as follows. I want to look at bivariate distribution. Simple command for a simple scatter plot is plot between parentheses x comma y, and the correlation is the last line core between parentheses x comma y. Okay, we see on the right the scatter plot for on the horizontal axis x and on the vertical axis y. This scatter plot looks like a distribution of two variables that are hardly correlated in a linear fashion, and it's therefore of no surprise that the correlation coefficient, linear correlation coefficient, is close to 0. Now let's run and compare a few simple regression models with response variable y and predictor variable x. So I'm going to make a note for myself of what we are about to do, competing models for predicting y by x. I call them competing models for predicting y by x because we are going to try to predict y by x, and we are going to compare these models in terms of a kind of balance between complexity and performance. So the first model we are going to run simply uses the average or arithmetic mean of y as prediction across the range of x, basically a flatline prediction. So I'm going to make a note for myself. This will be model 0, flatline prediction for all cases the mean of y. I call it model 0, and it's also referred to as the null model because it states no linear relation between x and y. Basically, it states no relationship whatsoever between x and y, so it simply uses a horizontal line. Now, the mean of y is something we can easily find with the mean function in R. Mean y, which is 0.023. Okay, so we have the mean. Now let's run the flat model or null model, which is basically a model that we define as this, LM, linear model, y by 1. It's a basically intercept only model. Okay, enter. Nothing happens on the screen because what you've done is just define a model. So now that we've done that, suppose we want to check the residuals of the model, which is something we always tend to do when we do regression modeling. So we have to, this was from the next model, we have to first use a line to define the residuals, flat underscore residual, residuals flat, and then histogram for the comment for the residuals. Hey, this is a fairly symmetric and unimodal distribution of residuals. Does not look horrible. So next we save the predicted values of the model for each of the 500 cases in the data file, and we request the outcomes in the left window. First line here, flat predict, is for getting the outcomes, for defining the outcomes, and the next one, flat predict, is just the outcomes itself. Scroll, scroll, scroll. We see all the 500 cases have the same prediction, which is 0.023, which is the mean of y, because this is what model 0 does. Next, model 1 is a linear regression model which describes the relation between x and y as a straight but non-horizontal line. Let me just run that, define that model linear as y by x. We can then define the residuals, save the residuals, and get a histogram of the residuals. Hey, this looks almost the same as the residuals of model 0. We can also get the predicted values. We want to save the predicted values and get them on the screen as well. Hey, we now see that each case has its own predicted value. That is no surprise because now y is a function of x. So any two cases that have a different value in x will have a different value, different prediction for y. Model 2, because model 2 is an extension of the linear model, but with a quadratic term, which is x2 that we defined before, remember? So we just defined that model. Okay, model is defined. We want to also have some residuals, and the histogram of the residuals, this looks pretty much like what we had for the previous two models. Well, let's also save the predicted values. The predicted values in this case, also different cases, different predictions for y. And then finally, we'll just do the same for model 3. I'll do this a bit more quickly. So model 3 cubic, function of x, x2, and x3. We are going to ask for the residuals, look at the histogram of residuals, and save the predicted. Well, again, as for the previous models, nothing horrible to see in the distribution of residuals. So now that we have saved the predicted values of all these models, we can create a chart that not only presents the actual data in the data file that we have been reading, but also the predicted values according to each model. So for this, we need to install a package that can help us to create nice graphs. And one of the packages that I like a lot, you will need to install it first if you haven't done it, but okay, I've already installed it, so I can just open it using the library command, library between parentheses, ggplot2, because this is the package that we are going to use. It's an amazing package because it allows you to make a very wide range of graphs, paintings, whatever you want, for all kinds of different models. I have just added a little bit of coding for the chart in the window. I will explain in a minute what these different lines stand for, just very briefly. Okay, I'll make this chart window a little bit bigger. So here we see the chart. We see it has a title, a subtitle, a description of the vertical axis, the description of the horizontal axis, and we see in this case the dots as the observed data, and the 4 dashed lines are the predicted values according to each of the 4 models in different colors, everything. So yes, this is in different colors because this is what I have told R to return. We have a chart 1, which is something with a title, 4 competing models for the prediction of y by x, a subtitle, definition of the axis, geom point, which is a line to define that we want something as points, which is in this case is y, so that's the data, and then 4 geom lines of line type dashed, which are the predicted values according to each of the 4 models. Then you see somewhere in the code I also say color equals something. So these are color codes. There are documents which give a very nice overview of all these different colors that ggplot2 has. I use those for all kinds of purposes. The last 2 lines are just simple lines because we want to have a just nice white chart with no grids or any colors. I'm not going to spend more time on on explanations for the ggplot2 package. There are loads of resources on that already, and it's beyond the scope of this specific video. But I wanted to show this package because it's a really nice package for creating charts. If you're using R or going to use R, I really recommend checking out ggplot2. So, okay, now that we have had a bit of time for the technical part, now let's just have a look at the chart itself. We see in this case that really the 4 different models appear to give very similar predictions across the range of x, which begs the question really how much more complexity than model 1 or even model 0 we need. After all, if more complex models provide substantially better predictions than simple models, preferring one of the more complex models may be justified. At the same time, if simple and complex models provide about the same predictions, we may as well go with a simple model. So now that we've seen the chart, I'm going to share 3 criteria that I tend to use for selecting the best of these 4 models that we have run. Model R squared, as well as Akaikis and Schwarz Bayesian information criterion. So I'm going to make a note for myself. I'm going to make the commands window a little bit bigger because we're not going to see more charts. Just a note for myself, comparing models using model R squared as well as Akaikis and Schwarz Bayesian information criterion. So what are these? Well, R squared is roughly speaking about the percentage of variation in Y that can be explained by the model and tends to go up as models become more complex. And this is where the two information criteria come in. They will prefer a more complex model only if the gain in model performance is substantial enough. The main difference between the two information criteria is that Akaikis criterion somewhat more easily indicates a preference for a more complex model than Schwarz Bayesian criterion. Let's have a look at this step by step. To start, I want a brief summary of each model, which can be done simply as following. So suppose I want to have a summary of the null model, a flat model. Now we have defined model 0 as flat, as the flat model or flat. Summary, hit enter. Okay, so we get the formula which we used before, some information on residuals, and then an estimate for the intercept, an estimate 0.023. Well, this is the mean of y that we saw before. Why is that? Because, well, that is exactly what model 0 does. Give the average of y as a prediction for all values of x. It doesn't give an R squared value because since it's a horizontal line, there is no variation in the prediction of y. The R squared value of this model is 0. Now, if we want the same summary for the linear model, for instance, or any of the other models really, what we do is, okay, summary linear, summary squared, and summary cubic. We hit enter. Hey, we get a summary for each of the three models. Let's go to linear for a moment. So for the linear model, we see, and again, for the intercept, we see an estimate, and also for x, an estimate. And we see a multiple R squared, which is the model R squared, which is 0.001218, which indicates that just over 0.1% of the variation in Y is explained by this model. That does not sound like a lot, and in research settings in the social sciences, for example, R squared values below 1% generally indicate small effects or weak relations. Next, we look at the R squared value of the quadratic and cubic model. So the quadratic model is 0.001271, the cubic 0.001598. So we barely see any improvement in the R squared value compared to models 0 and 1. So the question is, do we actually need a more complex model? And this is where the previously mentioned information criteria come in. So let's first do Akaikis criterion, Akaikis information criterion, also abbreviated as AIC. It's a criterion also like R squared that is provided in many software packages, including R, SPSS, Jamovi, JASP, several more. We get an AIC value for each of the four models. Now, for a model just in itself, the value doesn't mean anything. It's just only in comparison between different models, these AIC values make sense. So in this case, contrary to R squared values, the AIC lower AIC values are better. So in other words, here, model 0 is the best model according to AIC because it has the lowest AIC value. Although the other models logically have higher R squared values, the increase in R squared values with any of these alternatives is too small for AIC to prefer one of these alternatives. And given that, as I mentioned a minute ago, AIC tends to prefer a bit more easily a more complex model than the other criterion we are going to run, we should also conclude model 0 with the next criterion, Schwarz Bayesian information criterion. Wait, Schwartz information criterion. Well, let's just add a bit. Schwartz Bayesian information criterion for the 4 models. Okay, and indeed we see that according to Schwartz Bayesian information criterion, or BIC, which is also a criterion that is provided in most statistical packages, model 0 is to be preferred. Now, are these information criteria the only ways to compare models? No, there are many ways to compare different models, including variants of AIC and BIC for larger and smaller samples, statistical significance testing using p-values, likelihood ratios, and Bayes factors. Comparing, for example, model 0 and model 1, let's go to the summary of model 0 and model 1, yes, especially model 1 now for a moment. Model 1 provides a p-value for the linear regression coefficient, which is here 0.436. So this p-value was basically this line x is not present in model 0, because in model 0 the relationship between x and y is supposed to be non-existent, while according to the linear model that relation is linear. So here the p-value is far from statistically significant at the 5%. Now occasionally, if we use two-sided statistical significance testing in 5%, which we do here, AIC may occasionally prefer a model even if the p-value of the regression coefficient is just above 5%, for instance 0.08 or something, whereas BIC may occasionally prefer model 0 even if the p-value of the regression coefficient is just below 5%, so for instance 0.02 or 0.03. So I usually use R-squared in combination with both AIC and BIC, as well as underlying theory and previous research, to come to informed decisions. And one of the advantages of AIC and BIC relative to p-values is that it is relatively easy to present the outcomes of several models without having to present a range of p-values for each of these different models. Another advantage of these information criteria relative to p-values is that it is actually possible to compare models that have the same response variable but different predictor variables. So okay, here it does get a little bit technical, so I will stop about these differences between criteria here. I just wanted you to get a little bit of an idea how to use information criteria for model comparison. If you want to know more about these different ways of comparing models, just get in touch with me using the email address, which I will now type as a note in this window, and I will also leave below the video. You can get in touch with me for so I can give you some literature on this topic. That's it for today. Thank you for listening. And if you have any suggestions for further videos on linear regression or other statistical methods, you can always leave a comment below. Bye bye for now. I hope you found this useful, and I hope you have a nice day.